Hello, my name is Kim Gi-hyun, and I will present about synthesis of higher alcohols. The gradual depletion of oil resources and the necessity to reduce greenhouse gas emissions portray a concerning image of our contemporary security of liquid transportation fuels in the event of global crisis. Despite a vast amount of natural gas resources that we have and the huge economic incentive, the conversion of gas to liquid fuels or chemicals is still very limited because of the high technological complexity and capital cost for facilities. However, with the anticipated depletion of liquid petroleum and the soaring price of crude oil, the conversion of natural gas to liquid feedstock or fuels will become more and more important. Higher alcohols are important feedstocks for the chemical and pharmaceutical industries and have wide applications as potential fuel additives or hydrogen carriers for fuel cells for clean energy delivery. There is a long-standing interest in the synthesis of higher alcohols from syngas, an important Fischer-Tropsch technology for natural gas conversion. The highly dispersed cobalt metallic oxide pair has been regarded as the active site for higher alcohols formation. The cobalt metal cobalt carbide catalyst was tested free of promoters and suffered for higher alcohol synthesis. The results were in agreement with the widely accepted reaction pathway over cobalt monometallic catalyst that the synergistic effect of cobalt metal cobalt carbide is responsible for higher alcohol formation, with metallic cobalt active for carbon monoxide dissociative absorption and subsequent carbon chain growth, and cobalt carbide active for non-dissociative cobalt oxide adsorption and subsequent cobalt oxide insertion into the linear hydrocarbon intermediate. The interface between cobalt and each carbide phase provided efficient dual sites for higher alcohol synthesis. Unfortunately, it is known that monometallic cobalt catalysts during the higher alcohol synthesis reaction suffer from low thermal stability due to sintering of the cobalt nanoparticles. The agglomeration could also lead to the activation of the catalyst, resulting in a charge in catalyst performance. It was found that the cobalt-copper alloy was formed at first as the active center after reduction, but started to decompose into copper and cobalt species at the beginning of the reaction. As the reaction continued, smaller cobalt nanoparticles started to be enriched on the surface of copper nanoparticles, resulting in a copper-cobalt coaxial structure. After reaction for 300 hours, sintering of copper led to enlargement of copper-cobalt particles, and carbonization of cobalt resulted in the formation of cobalt carbide. At this stage, the active centers were transformed to copper-cobalt carbide. During the end of the reaction period, the copper and cobalt nanoparticles were wrapped by cobalt carbide. The higher alcohol sensitivity during the whole reaction process is mainly due to the close contact of copper and cobalt species, including copper-cobalt alloy and copper-cobalt nanoparticles. Furthermore, significant deactivation of the catalyst during the reaction was also observed. In addition to the cobalt-copper phase separation and cobalt luge, sintering of the active metal copper and cobalt nanoparticles is considered as another factor that led to the deactivation of the catalyst, which was different from the above-mentioned perovskite structure-derived cobalt-copper bimetallic catalyst. Cobalt-copper niobium trimetallic catalysts have also been targeted by researchers to form C2 to C5 alcohols from syngas. The bimodal nanosized particle distribution was achieved in cobalt-copper niobium catalyst with smaller niobium oxides acting as a structural spacer to enfold the larger cobalt-copper particles, which results in an increased specific surface area. Besides, the strong metal support intercalation between niobium 4+ ions and metallic cobalt led to an enrichment of cobalt on the cobalt-copper particle surface, which could increase the concentration of surface CHX species for higher alcohol formation. CO conversion with all cobalt-copper based catalysts under low temperature reaction conditions remains below 20%. While it may seem appropriate to develop catalyst formulations providing higher activities, one has to keep in mind the considerable exorbitity of the process and the need to develop suitable means for managing the heat removal from the reactor. While some progress has been made, a number of challenges still need to be overcome to further advance the direct synthesis of higher alcohols from syngas. First, most of the higher alcohol synthesis catalysts exhibit a trade-off between selectivity and conversion, leading to low yields of higher alcohols. Second, higher alcohol synthesis catalysts suffer short catalyst lifetimes due to the deactivation problem stemming from metal sintering or phase separation. Third, the higher alcohol's production costs are high, including catalyst preparation and energy-intensive operation at high temperature and pressure. Last, the nature of the active centers remains ambiguous because of the complexity of the reaction pathways and the limitations of the characterization method. Thus, further improvements in the development of higher alcohol synthesis catalysts are still urgently required to achieve higher yields of C2 plus OH alcohols for industrial application. Thank you for listening, and here is the reference.